Hello everyone and welcome to Pre-Calculus. We start here in Chapter 1, which is a nice chapter because it's pretty much a review of what you've done previously in Algebra 2 last year. So we start in Chapter 1, which is called Functions and Their Graphs, which we did again in Algebra 2. So Section 1.1 is just all about functions. If you remember from Algebra 2, what a function really is just basically thinking about like a vending machine. Okay, so before I even think about the word function, let me take a step back. And let me think about, first of all, it's called a relation. A relation is when you take two things that are mapped together. An input, for example, when you input money, I'm going to drop in a dollar bill, and the output is what comes out of the vending machine. So the vending machine is a really good example of what's called a relation because you can put in any kind of money, and what comes out is your output. So money here is your input, and whatever you get, whether it's a bag of chips or a can of soda, is your output. Input and output. Now you can put different kind of money in, and also when you choose, you can get different types of food out. If you put $1, you have a lot of choices with $1. So that's what's called a relation. And there's another way of showing it here. Another word for your input is called the domain. Do you remember that word? So this is your domain. That's the money you put into the vending machine. And your output, the chips or soda, is called your range. So just another fancy word for input and output. But we'll use domain and range a lot this year in pre-calculus. Now notice what these arrows and dots are doing. This is almost like here is the money, I'm putting it in. And what do I get over here is I get something in your output, whether it was the bag of chips or the soda. So different spots in my domain are giving me different spots in my range that are being paired up. And there we go. Just like it says up here, a relation is basically a mapping or pairing together of input with output values. But now, what if by chance, if you put in an input of, say, money, but you only push the buttons B1, for example, which is, of course, extra cheese Doritos, yes. When you push that button, you will only get one output out. You will not get the Doritos plus some Chips Ahoy. Although that would be sweet, you usually don't get that on a vending machine. So again, to review, you get your input, which is your dollar. You push a button and you only get one output, not two choices. You only get one output. Well then, guys, you have something very special called a function. A function happens when, for every one output for each input. So each input you have, you get one and only one output, and that's called a function. So let me show you a couple examples. The vending machine was a pretty good example. Here's another one we can do. First of all, for number 1 and 2, can we identify what is the input, what's the output? So therefore, what's the domain and what's the range? And then, based on that, can we figure out if this relation is a function? Okay, so for number 1 is definitely a relation, right? Because we're mapping inputs into outputs, looking at all the different arrows. This is sort of a column bubble format. And you see that the -3 over here in the inputs being mapped to the 3, and so on and so forth. So my domain here, I'll just put a D here. The domain is the same thing as input, right? So -3 is my domain, 1 is my domain, and 4 is in my domain. So therefore, how about my range? Range is the same thing as output, right? So my range values would be 3, -2, 1, and 4. Okay, take a look here, folks. Is every input going to one and only one output? Let's see. The -3 is going to a 3 and nothing else. Down here on the bottom, the 4 is going to a 4 in the output, nothing else. But will you look at that 1? Do you see how the 1 is going to both the -2 and the 1? That's not allowed. This is still relation, and that's okay, but is it a function? No, not a function. You need to have one input going to only one output, and that one over here in the domain cheats, goes to two different outputs. Another cool example of what's a function is think about the time of day and the weather outside. That's actually a pretty cool function. So if I use this example that we have here, if 1 is my time, at 1 p.m., is it possible to be both -2 degrees outside and 1 degree outside? That'd be very, very strange, right? So you can only have one output for each input. All right, that's number 1. You want to try number 2 on your own? Why don't you go ahead and pause the video and give it a try. All right, friends, here we go. Domain. All the input values would be -3, 1, 3, and 4. So all my domain values, my input values here, and then my output values are my range. 3, 1, and -2. Take a look and see how are the inputs being mapped to the outputs. And everything looks okay. Every input is being mapped to only one output. So is this a function? Yes. But do you notice something a little strange about it? Because there is something that makes me think maybe it's not. And it's right here. Did that bug you? Because it kind of bugged me too. Do you notice how the 1 in the input is going to the 1 in the output? And the 3 is also going to the 1. That's weird. That's 2 inputs going to 1 output. But go back to our rule up here. Is the input going to only 1 output? Yeah, it is. It still is. Go back to that weather idea. If the time was 1 o'clock, and therefore the weather would be 1 degree, is it possible for it also at 3 o'clock to also be 1 degree? Is that possible? Yeah, that is possible. It does feel strange because we think it's not a function, but it really is. So there you go. That's how you can first look at here at different examples of inputs, outputs, and see if they're ranges and domains, and see if they're functions. Now, I would like to do this in a more graphical way. I like this way, but I like coordinate planes and stuff. So what we're going to do is we're going to take number 1. We're going to erase all our work here. And I'm going to change this from an input-output table into XY coordinate points. Meaning, you see that -3 goes to 3, right? So that would give me -3, 3 as a coordinate point. Let's keep going. The next one, the 1 in the domain goes to -2. The 1 also goes to a 1. That's what makes it not a function. And the 4 goes to a 4. So I've made 4 coordinate points. I'm going to map those in just a second. But while we're doing this, why don't we go ahead and do it on the right side for number 2. All right. We have -3 going to 3. We have 1 going to 1. We have 3 going to 1. And we have 4 going to -2. All right. So on the next page, why don't we go ahead and make a couple graphs. Let's see, how can we tell if these were functions not by looking at the input versus output, but just looking at the graph. Let's try number 1. All right, number 1, I'm going to graph -3, 3. I'll be flashing back and forth so I can see my points. 1, -2, and 1, 1. 1, -2, and 1, 1. Kind of reminds me, make sure we're comfy with graphing points, knowing they're going X direction, which is left and right first, and then your Y direction, which is up and down. My last point is 4, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, that's number 1. Let's go on graph number 2 while we're here. That was -3, 3, and 1, 1. So again, -3, 3, and 1, 1. And we also had 3, 1, and 4, -2. 3, 1, and 4, -2. All right, friends. Now, we already figured out before that this one is not a function, but this one is. So as a word, can we look at these 2 graphs and notice what's different about them? What makes the one on the left not a function, but the one on the right also a function? Well, remember, these are both relations no matter what, because we're still mapping inputs and outputs. But are they functions? Now, left one's not. I wonder if you notice that something funky is happening right here. Do you notice that? How 2 points are appearing on the same vertical line? But that doesn't happen anywhere here. Over here on the left, the reason why that's happening is because for this input of x equals 1 and this input for x equals 1, I'm getting 2 different y values. And that's what makes it not a function. So visually, what did we see? We saw a line that goes up and down, which we call a vertical line. We didn't see that over here on the right-hand side. We do sort of have this funky horizontal line that goes to the 2 points. But is that bad? No, that's okay. We can have that. It's this vertical line over here that we're a little bit nervous about. Do you remember that out from Algebra 2? That's how we can test and see by looking at a graph if it's a function or not. We called it the vertical line test. Yay, something from the past. So you can say that a relation is a function by looking at a graph. And if you can tell that a vertical line goes through only 1 point at a time, then this guy is totally a function. If the vertical line goes through more than 1 point at any spot, he ain't a function. So So let's test down here. Oh, if you can kind of squint your eyes on number 1, can you tell me if that's a function or not? Well, just sort of mentally, you're sort of making a whole bunch of vertical lines through the graph. Does it ever go through more than one point? No, it doesn't. This guy is totally a function. He's okay. He's good. How about for number 2? Is this beautiful heart graph, is it a function? Well, let's see. Can we draw a vertical line? And if it ever goes through more than one point? Well, gosh, unfortunately, it's almost through the entire thing. Right there, for example. Over here. Poof. And if you do you see how you're going through more than one point? So therefore, unfortunately, love is not a function. Sorry about that. So now that we can identify functions, let's see how we write them. Functions, we usually write using this cool notation, the f parentheses x. And the way we say it is basically we just say f of x. That's how we actually say that in words. What that really means is when you plug your x value in, what is your y value? That's basically what that means. Almost like the vending machine. When you put in your dollar bill for x, what kind of food do you get out? The f is like the y value, and the x is your input value. So what's the value of the function when you plug in x? Which means now I can go back to my opening diagram and say now domain, which is the inputs, are like the x values. X is what you're plugging into the function. And what you get out are the f of x values, or also called the y values. These are the same thing basically. So f is pretty much like y. All right, well, let's play with these a little bit. Now that we know how we can write them, what are we allowed to plug in? What is the domain of a function? If I give you an expression or an equation, what's the domain? What are we allowed to plug in algebraically? For the most part, if you see here, for most functions in algebra land, you can plug in anything you want, and we call that all real numbers. You can plug in negative numbers, you can plug in positive numbers, you can plug in 0, anything you want. It's all real numbers. And we write it like that, or we can use the cool little shadow r. I'm not sure if you learned that in Algebra 2. But that little shadow r means all real numbers. What's the domain? Oh, anything, all real numbers. However, there are two really, really big exceptions in algebra that we have to be really careful of. And it's linked to what we are not allowed to do in algebra. Sometimes I refer to those as danger zones. First of all, you have to be really careful. Remember that we can never, never, ever divide in a fraction by 0. That's bad. We can never do that. Dividing by 0 is evil. So we want to make sure that if we have a function that is a fraction with an x or x expression in the denominator, we have to make sure we avoid this from happening. So if you just look at this example here, friends, can you think of what x value could you plug in? And you would get 0 in the denominator in the bottom. Well, what could I plug in here that would make this whole denominator equal to 0? I think it would be 7, right? So x equals 7 is a really bad number here, because plugging in 7 would give you 0 in the denominator. We can't do that. So all your domain values would be anything in the world, but just not 7. And so this you actually write as your domain. What's the domain? Oh, okay. All x's that are just not equal to 7. And that's your domain. Okay, that was a pretty simple one, but what if it got a little more complicated? For example, if I say f of x equals 1 over x squared minus 4. All right, do you notice first of all, danger zone, danger zone. I do have an x expression in the denominator, so I have to be careful there's no 0 here. Well, here's some really good steps if you want to think of it in a real simple way. Basically, take your denominator and set it equal to 0 and solve. And those are going to be your bad x values. So what I'm going to do is I'm going to take x squared minus 4. I'm going to set it equal to 0 and find out what x values do I get from there. That's really bad. If you remember from your algebra days, this is totally factorable. So I'm going to factor it. This is what we call the difference of squares. And that means if I solve each parentheses, x equals either positive 2 or negative 2. Great. Okay, so those are the x values that would give me 0 in the denominator. Do I want them? Heck no. So my final domain here for this expression, all x's just not equal to plus or minus 2. Everything else in the world is totally legit. I can plug anything I want here. I cannot plug in plus or minus 2. That's one type of danger zone. The other one over here, again, remember in algebra, whenever you have a square root or any kind of even root, remember what kind of numbers we're not allowed to put inside there? Positives are okay. You can take the square root of a positive number. And you can actually take the square root of 0, but we cannot take the square root of negative numbers. That's very bad. For example, the square root of negative 3. Just not a real number. And in function land, we're talking about real numbers. Do you remember from last year? This would usually give you some kind of value that we called I, the imaginary numbers. And we usually don't do that this year in pre-calculus because we're dealing with functions that deal with real numbers. All right, so how about something like this? If I give you f of x equals the square root of x minus 1. So in your brain, a little bit of a danger zone. Watch out, I've got a square root here. I have to be really careful. All right, here's another set of steps over here that are really helpful for me. If you want to figure out what values can you plug in, well, let's take this expression out. Rip it out. Rip it out. X minus 1. That thing cannot be negative, right? So what we're going to do is we're going to set it everything else. We're going to set it either positive or equal to 0. That means it's not negative. So these are the values that I can plug in. And then let's just solve. So if I move the 1 over and I add it, I get x is greater than or equal to 1. And there you go. There's your domain. For this expression here, the domain is all x's that are greater than or equal to 1. And that's okay. That means anything that's less than 1 is not legal. But anything greater than or equal to 5, 15, 2 million are good to go. Let's try one more. How about f of x equals the square root of 2 minus 3x? All right, why don't you go and pause, and can you solve this one and find the domain on your own? Good luck. All right, welcome back. So danger zone again, you see that you've got a radical, a square root here. So we're going to rip out what's inside and set it greater than or equal to 0. All right, now we solve. We could do this by maybe subtracting the 2. So I get negative 3x is greater than or equal to a negative 2. Now I'm going to divide by negative 3. So just be careful. If I'm dividing by negative, a good review, do you remember what happens to your inequality here? It flips. So I should get x is now less than or equal to, because I divided, or if you multiply, by negative. Negative 2 over negative 3, the negatives cancel, and I just get positive 2 over 3. And that's my domain. My domain for this equation, or this function, is all x's that are less than or equal to 2/3. Anything bigger than that does not work. And you can test it out. If you actually take the number, say x equals 5, which is bigger than 2/3, and you plug it in up here in the function, you're going to notice you can get a big negative number inside the radical, which is not a real number. So you can tell that that answer works. X is indeed less than or equal to 2/3. Good job. So that's how we can find the function domain algebraically. But how about more visually? Can you look at a graph like this, guys, and see if you can find the domain visually? Last time was algebraically. This one's visual. Well, remember, if domain is the same thing as x, that means we're traveling along the left and right of a graph, along the x-axis. And vice versa, if you're doing the range of the y values, that's up and down. So if I ask you, friends, we're looking at this little chunk of a graph here. Here's f of x. Here's our function. And I say, what's the domain? You're going to tell me how far left and how far right is this guy traveling before he stops. And similarly, if I'm asking you the range, I'm asking you how far up and how far down he's traveling before he stops. All right, let's try it. Let's see if we can figure out what's the domain of this function. Well, how far left does he travel? As I go all the way to the end of it, he stops right here on the left. And what x value is that? That's x equal to 1. Okay, so it seems like he goes all the way to 1. And how far to the right does he go? He goes all the way to the right, up here. And I said up here, but that's kind of a little bit tricky. I meant to say really to the right. Up is going to be a range question. So how far to the right does he go? That's, I think, all the way to 8. So I can write it like this. My domain are all x values that are less than or equal to 8 or greater than or equal to 1 using inequality notation. Notice I put the equal sign here because if you notice at the endpoints, they are real dots. So the points do exist. Versus if you remember from algebra, if there was, for example, a hole in the graph, like over here, a hole means it wouldn't exist. So you would use one of the inequalities that doesn't have the equal sign. So, and at 8, it does exist as well. Now, I like that kind of notation, but I also like this. If you remember interval notation just writes it like an interval. I go from 1, comma, to 8. Those are the x values that I play with. Now, I am equal to 1, so I'm going to put this hard square bracket here. And I am equal to 8, so I'm going to put a hard square bracket here. And bring your eyes back over here, friends. Remember, if it was a whole, not only do you use the sort of open inequalities, but we use the parentheses in interval notation, not the hard brackets. All right, good little algebra review for you, friends. How about the range? How far up and down does he go? Well, it looks like the lowest point down here is at y equals 2, and the highest point up here is also at y equals 8. So now I can use my inequality. But remember, this is an x, this is range, so y is less than or equal to 8 and greater than or equal to 2. Or it's between 2 and 8, bracket, bracket, because they're equal both points. There you go. You want to try this one on your own? I have a special word here on the bottom. Do you remember this from your Algebra 2 days? Can you find the zeros of that function as well as the domain or range? Okay, good luck. All right, my domain again are my x values. So domain, I'm looking left and right. How far left does he go? And if I count on my little hash marks here, 1, 2, 3, 4, 5. Looks like he goes all the way to 5. But you notice that open circle? That means he doesn't exist. But we put -5 anyway. But we're going to put it 2 ways. I'll do the inequality notation. He is greater than -5, not greater than or equal to, because of the whole. So x is greater than -5. Then how far to the right? All the way over to here, which I believe is 7. So, and it is a dot up here. It's a solid dot. So x is less than or equal to 7. Or inequality notation, how about -5 to 7? Sorry, interval notation. Now equals 7, so square bracket, but it doesn't equal -5, so we put the parentheses. Either answer is great. I like this one because it's just a little bit more compact, and we don't have to use inequality notation there too. Okay, the range, how far up and down? Well, the lowest point is down here, which is at -4, and the highest point is up here, which is 9. So the range, again, y values, it does equal 9, so I'll put less than or equal to 9, but only just greater than -4 because it doesn't exist at -4. It's an open circle. Again, interval notation, how about -4, comma 9, square bracket on the 9, because it's a dot, but parentheses on the -4. All right. Zeros. If you remember from last year, zeros are the same thing as the x-intercepts, or the x-solutions, or the roots of an equation. They all mean the same thing. But for this graph, think of them in terms of x-intercepts. So where do I cross the x-axis? Let's see. It looks like I cross over here, and I'll cross the x-axis here, and over here. Oh, okay, there's 3 of them. So my zeros would be at x equals, let's see, the first one on the left looks like it's about -2.5 or so. And keep going left to right at 1, 2, 3, maybe x equals 4. And then also x equals 5. Those are my x-intercepts. So I can also say those are also my zeros. And there you go. There's a good start. At the next video, we're going to talk about how we can actually plug values into the function. What does that mean? Both algebraically and also on a graph. And leads to the crazy difference quotient from calculus that we'll take a look at in the next video. Great job today, everybody.